And this is done with Sitadi Roy and Vikram. So I would like to thank the LTVSP organizers and of course Sitadi for giving me this chance of working on a project. And so the project is about connecting the fog to real. So we are trying to connect two quantities, one in the fog space and another in the real space for a in a disordered spin chain. So, so a general question in the condensed matter physics or statistical physics is to understand the systems which are defined by Hamiltonians, which have on-site energies, hopping terms, and the interaction between the particles. So much of the work which has been, such a Hamiltonian, which has different on-site energies, so depending on the strength of the interaction and the strength of the on-site energies, we can have localized or a delocalized phase in such systems. So far, these sort of systems were studied in this using the real space functions like 2-point correlators or a real space correlation length. And that we try to connect with some quantities of interest like transport of charge or transport of or any conserved quantities. But and the benefit here is that we can connect these quantities to some other quantities which we can experimentally measure. But the another way to really tackle this, another direction to tackle this problem is using a fog space framework. So since we are dealing with the many body phenomena, fog space gives us a natural framework for studying systems, but there is an extra benefit that it's an easier framework for systems having local as well as non-local interactions. So any many body phenomena is like a single fixitious particle moving in this fog space graph. And that's what we will try to, and we can also use fog space correlators, like we have correlations functions for real space. We can have fog space correlators to define functions in this fog space space or framework. So let's start with how we'll move from a many body system to this single particle space. So we have this many particle Hamiltonian. The first one has the on-site energy, on-site potentials, Hi, sigma, Z, and there is this hopping term. The second term is the interaction term in the Z direction. So I can map, and the first term is actually the Anderson Hamiltonian, which is just for a single particle Hamiltonian without any interaction. I can map such a Hamiltonian to a single particle Hamiltonian. So I can write that Hamiltonian in the basis of in the basis of sigma Z product states, which is actually the different spin configurations which can exist in the real space. So if there are L sites in the real space, there will be 2 to the power L different spin configurations in the fog space. And you can see that this Hamiltonian has this on-site energy, which is given by Ej, and this hopping term, which is given by Tjk. That's the energy that it takes from going from state J to K. And you can see that this is actually related to this Anderson Hamiltonian, which has the on-site energy and the hopping term in the real space. We can also understand this with this graph, where these nodes actually denote our sigma Z product states, and this Ej, epsilon J, epsilon K are the on-site potentials, and Tkj is the hopping term. So we have 2 to the power L nodes in such a graph. We can also define this notion of distance in this fog space, which is, let's say I have taken a state which is all up spins in the real space, which is denoted as a yellow block in this slide. So this yellow block is actually a node in the graph that I've shown you. Let's say it's a node J. So any other state which is different from this yellow block by one spin flip is at distance 1. or any other state which is different from this yellow block by 2 spin flips is at distance 2, which is I have denoted by r equal to 2, and so on. So this way we can define this notion of distance in the Fock space graph. And we can analytically define the Hamming distance by this 1/4 sum over the different spins at different sites. Okay. So now that we have set a stage of how we move from a many particle to a single particle problem, now let us see what all quantities that we are interested to relate the two framework. So so let's say in the real space, I have certain spin configuration. Let's say at the site 1, the spin is up. This state, when it evolves with unitarily evolves with time, will become a superposition of different states where the spin 1 is either up or down, or or different permutations of the other spin configurations, like other L-1 spins. So we define here this autocorrelation function, which is the correlation between the spin at any site. Let's say I've taken 1 with the same site at some different time. And I can take the average. So I have defined it with the trace of sigma I z t, sigma I 0, and then I can take the average over all of the sites. So this correlation is actually a measure of memory. So as I told you, like this disorder Hamiltonian can either be in a localized or a delocalized phase. So in a localized phase, as at t tending to infinity, there will be a finite memory that it will remember its initial state. But in a delocalized phase, there will be no memory. It will slowly forget its initial configuration. So this is the dynamics for the real space that we are interested in. Let's talk about the dynamics in the Fock space. So let's say I have taken this, as I've shown you this slide before, this graph before as well. So let's say I have this yellow block, which is my initial state, which is actually all the spin up state in the real space, but this is actually a node in a Fock space graph. So with time, the state will, so let's see this way. So at initial state, we have a delta function at this node. With time, the state will evolve, and there will be different weights in the different nodes of the graph. So return probability is this evolved time, evolved state I naught. What is the weight of this evolved state I naught after some time t? So this also encodes the memory of the initial state, which is in a different framework of a single particle in a graph. So because both of them are actually a memory measure, it's interesting to now see like how they are related. So, and also return probability at t tending to infinity will be 1 by total number of nodes. Because this is in the delocalized phase. Because in the delocalized phase, the wave packet will evolve and it will spread with time, it will equally spread in all of the nodes. So in the initial node, it will be 1 by 2 power L. So for this understanding this dynamics, we have taken a disordered Floquet model, which is actually a discrete periodic disordered Hamiltonian, where we are switching between the Hamiltonian Hz and Hx, and the time period is of t, is the time period. And so the system will evolve in this time period t by 2 Hamiltonians. So first it will be by uz t and then ux time evolution operator. So this overall operation, this overall evolution is given by a Floquet operator, which is actually the product of two operators. So in this system, you can see that for half of the time period, there's a disorder is denoted by GI term. I don't know how this laser works.
It's left.
Okay, this disorder term is given by GI, and gamma is the tuning parameter. So gamma is if my gamma is less than 0.3, I'm in NBL phase. If my gamma is greater than 0.3, I'm in the ergodic phase. The point of taking such a Hamiltonian is like there is no conservation loss, so all of the nodes are equally accessible. So for the real space dynamics, we get this numerical result. As you can see, is actually a stretched exponential. This is the autocorrelation, which is disordered, averaged over many disorders. And it actually goes to 0 at t tending to infinity, but this is a like for a finite system, so it will go to a finite value. For the Fock space dynamics, I have return probability, but it seems to depend on the length as compared to this autocorrelation function, which is sort of independent of different system sizes. So, so instead, we actually look at the quantity, which is RT1 by L, which is, you can see, is now independent of L. So, and also this return probability in the infinite time limit actually goes to a finite value. But that return probability that I told you actually goes to 0. So instead, we are interested in the quantity RT by R infinity, and this will actually go to 0 in the infinite time limit. So we have two quantities, CT, like two thermodynamic quantities is autocorrelation function, and the other one we are interested in is ln RT by R infinity 1 by L. So now the question is how they are related. So in the summary, I told you like how we move from a many body Hamiltonian to a single body Hamiltonian, and the quantities that we are interested to make this connection were autocorrelation function, the return probability, and the thermodynamic quantities are CT and RT to the 1 by L. And now we are interested in how they're actually related analytically. That will be explained by Bikram. So that's it. Any questions?